to a well-formed hierarchy. So that's problem number one. I haven't rolled out cycles. Problem number two is uninterpreted functions are total in SAT. They are defined on every single element in your domain. So my entity store representation in the SMT world is infinite. I have to convert that to a finite counterexample and also somehow rule out these cycles that I didn't explicitly rule out because they were not in my footprint. How am I going to do that? So the insight here is that the SMT solver, when it gives you back a model of an uninterpreted function for a quantifier-free formula, or a quantifier-free, it's not going to emit an arbitrary function. They're all going to look a certain way, and that certain way is they're going to look like a lookup table with a default value. Okay? So it's going to enumerate all the exceptions on top using these if then else statements, and then the final else is going to be the default value. So the range of the function is finite, even though the domain of the function is infinite. Okay? So we can use the finiteness of the range to emit a finite counterexample. Now, for the things that are not that contain cycles, note that if something is not in the footprint, it cannot affect policy semantics at all. We can therefore replace all of these things with the empty set. So we're going to repair the model returned by the SMT solver, and then using this trick of mapping the finite range into a finite counterexample, we're going to extract a counterexample here that looks like this. Okay? So this is how the SMT translation works. So I proved that this entire thing, this is fully executable, again, you can write it yourself, is something complete. Meaning that any analysis that you build on top of this compiler, so equivalence, things are not false, things are always false, things are always true, and a bunch of other ones. The analysis is not going to give you any false negatives, it's not going to miss any bugs, and it's not going to give you any false positives. Because of these constraints that we're emitting and the way that we're extracting counterexamples, we're guaranteed to give you a true counterexample if one exists. Okay? So that's what it proves. All right. So that's safety and analyzability. We're now going to talk about performance and how we build Cedar, the differential testing part. So if you were using Cedar in production, you would run the lean code, which makes me really sad, but you would run the Rust code. So if you're using Cedar in production, with the within your application, you use the Rust code, and the flow sort of looks like this. You select your subset of the policies that's relevant, subset of the entities, request, you pass that into the Cedar authorizer, and it's going to come back with allow or denied and a bunch of diagnostics that help you figure out why the request was allowed or denied. This is actually really fast. It takes less than 10 microseconds to evaluate a typical Cedar request. This is much, much faster than existing authorizers, so anywhere from 30 to 80 times faster than existing authorization languages. So we built Cedar to be really fast. Now, Rust is very nice. It's a beautiful language, and it gives you speed, nice, and memory safety. But of course, it doesn't give you, you can't prove anything about the semantics of your program. So this is where differential testing comes in. So every single component of Cedar I talked about today, okay, the authorizer, the evaluator, the type checker, the symbolic compiler, we built every single one of those things twice. Once in Lean, once in Rust. And we use differential testing to check that the Rust implementation matches the Lean model. So how does that work? Well, we have lots of machines that every night for 6 or more hours are going to randomly generate millions and millions and millions of test cases, which they're going to feed to both components. In the case of the authorizer, the test case consists of a request, some entities, and some policies. It's going to feed them to Lean, it's going to feed them to Rust, it's going to get the outputs and compare them. If they're the same, you have found one piece of evidence that Rust does the right thing compared to the specification. If not, you found the bug. Okay? So this is how the differential testing works.
When you generate them, how do you make sure you're searching the possibility space well and not just trying a million
Yeah, yeah. We use TurboFuzz, which guides the fuzzer to maximize the coverage of the Rust code. And we have lots of smart skills into the generators because, if you think about it, the Cedar input is pretty complex, right? If you don't do this carefully, you're just going to generate a bunch of policies that are going to fail because of errors, right? Like you type incorrect things and whatnot. So we do have smart test case generators that are also driving the coverage towards as much of the coverage of the Rust code as you can. Okay. So specification in Lean, fully executable. The code is in Rust. The Lean code is built for two purposes. One purpose is to really be the official, readable, and provable specification of the language. You can sit down and understand every single component of Cedar if you look at the Lean code in a few hours. It's 5,000 lines of code, and that's actually a really small amount of code when you think about what all that code is doing, right? It's like providing a full interpreter for the language, a full type checker for the language, a full symbolic compiler for the language. So a nice thing about Lean is it lets you write code very succinctly. So 5,000 lines of code. The Rust implementation does more, right? So, when you're running something in production, you have to have nice diagnostics, nice error messages, all sorts of things that you don't have to worry about on the Lean side, and the code is much, much bigger. What we have proven on the Lean side is a bunch of things. So for example, we proved that the authorizer is default deny, the property that I told you. Deny trumps allow. The policy slicing and entity slicing are sound, the algorithms that we give you to do that. The validator is sound, and the symbolic compiler is sound and complete. So all of these proofs are 39,000 lines of code. But still not bad, right? Like all the proofs plus the specification is less than the production implementation, so still pretty good, right? And this process is very effective at finding bugs. Some of the more interesting bugs that we found were in the design stage. So, when we design a feature, we model it in Lean and we try to do it correct. Sometimes we didn't do the design right and the proof would fall through. We couldn't do it. And we were able to fix it before we reached production and even in the implementation. And finally, we found a bunch of bugs with DRT or the Rust and Unicode disagreed. And these are all, numbers as of, a few months ago. They're probably gone up by then. So the code is extremely well tested, battle tested, and it's very stable. So this is an effective way to kind of get the best of both worlds. Your implementation in a mainstream programming language, but your design in a theorem proving language so you can prove its correctness. And questions, as many questions as we can fit in the rest of the lecture. What we're looking into right now, and this is a...
If you had a language that had the verification capabilities of Lean, but also the low-level capabilities of Rust, would that have been helpful?
Totally, yeah. So what we're looking right now, and it's a very pie in the sky idea. I don't know if I'm still being recorded by it. It's like, okay, very pie in the sky idea is we're looking into using Verus, the Rust verification tool, to show that the Rust implementation satisfies the functional specification. Then theoretically, you could inject that functional specification into Lean using some trusted bit of code, and you can connect that to the metadata table in the proven. So that would let us reduce our reliance on differential testing. But you're right. If somebody came and gave me a tool that you described, I would totally take it. Yeah.
Right. So it seems you had to write everything twice.
Yep.
I was wondering, was it really just hard to generate the Rust from Lean, or is it, oh, we could generate the Rust from Lean, but it would be really slow? Like, did you have to manually write both of them? Wasn't there anything you could do to bridge it a little bit easier?
That's an excellent question. We manually wrote both of them. There is another group, team at Amazon that did the compiler approach. So they actually wrote their system in Daphne and verified it. And then they built a custom compiler from Daphne to Java. The reason why a normal code generator would not work in this case is that people will not run the code that they do not understand. So your compiler has to generate idiomatic code. Writing a compiler that generates idiomatic code from one language to another is super hard, especially when there is a massive semantic gap between something like Lean and Rust. Like Daphne and Java, they're very, they're close enough, right? Object-oriented, but Lean and Rust, super big gap between those two.
Yes. This is sort of in reference to the first question you had. A single language. Even my experience with Lean was that even if I have there's a split between the language and the peer movement side, functional language side, do you think that it would still be just as hard even in a single language? It seems like there's no system out there that puts them together.
Oh, yeah. There's no free lunch. Like, the proofs can still be hard, but it would be nice not to have to do everything twice. We probably still have to do it twice, to be quite honest with you, because
This is what I think.
you would have to do a functional specification and then an imperative implementation that's fast. But the nice thing is that once you do it, once you take that hit once, you don't have to, on top of that, also rely on random testing to connect it to. So if we could make that connection formal, that would be quite nice. But it would not be any less work. It would just give us extra peace of mind. Yes.
So I think it's very impressive that you implement first in Lean and also in Rust, so you can really test, you can show that it's sound. So my question is, there's a problem that when we do these formal verification is that these proofs are very fragile in the sense that if you want to extend maybe the Cedar language, maybe you add optimization, maybe the whole proof just breaks and you have to spend a lot of time just fixing those. I was wondering whether you encountered this kind of problem when maybe you want to extend the language and you have to fix it, and does it take a lot of time, or if not, how do you mitigate these problems?
Mm-hmm. That's actually an excellent question. So Cedar has been around for 3 years now, and we have extended it several times during those 3 years. So some of the proofs it turns out that our proofs are quite stable. We don't have to do a lot of work to go from one version of Lean to another. So we follow a specific set of proof engineering guidelines that ensure proof stability at left level. So from one update to another. But from one language feature to another, that's actually a really good question. And it could be quite bad, especially for the symbolic compiler, because that is an extremely complicated piece of code, right? It's like doing this matching between these two very different semantics, right? Cedar and SFT. So for that, the compiler proof is organized in a specific way that allows us to make little localized proofs for a new feature without affecting the global proof and having to change everything. So I know this sounds pretty vague, but you're right, it is a real problem. And we have designed our proofs in specific ways to make sure that this doesn't bite us too much, right? Obviously, if you change something completely fundamental about the language, everything goes out the window. But for extensions, just additive features, it's actually fairly modular. You just add proofs for that particular feature that you added and plug it into the rest of the proofs, and for the most part it works out. To give you a concrete example, I built the entire compiler of the proofs for one version of the language. Several features were added after that. One of the features was added by somebody who's never seen Lean or our code, and he did it in a week. So because of the way that we organize our proofs, I basically told him, hey, here's a piece of code, here's a part of the code base that you have to touch, and nothing else. And he did it, and it worked out. So it can be, so one of the things that we have to worry about, and we have to be very careful in the industry when we do this, is all of these proof engineering concerns. Like it's not like a paper. You write a proof and then you forget about it, it just goes stale. We have to live with that proof for as long as the language lives. And those are the concerns.
That was actually a very concrete answer, so thank you.
Yeah.
I really appreciate you talking about the CC challenges of bridging the gap between Cedar and SFT world. One curious thing would be any interest in a different kind of solver or a custom solver
out of the language, because if we express them in the obvious way using the SMT construct that already exists, we cannot convince ourselves that we remain in the decidable fragment. But when I talk to SMT people and I describe the problem, they say, ooh, that sounds decidable. And I'm like, okay, so when somebody proves that it's decidable, we'll take it in. So it'll be actually quite interesting. There are quite a few interesting extensions of SMT, or somebody sitting down and proving that a fragment that I would use in my translation keeps us in the decidable fragment. We would absolutely do that. Yeah. Yes.
I'm curious on the mean side for differential random testing. What's your approach to modeling the SMT solver?
Oh, right. So I have manually written a term language. So the proven part is between Cedar and the term language, and then the trusted part is the extraction from the term language to SMT. But that extraction is pretty straightforward. Like, you can look at the code yourself. It just like walks down the term AST and emits those declarations and assertions in it.
Okay, so you're saying that you use the SMT solver on the lead side?
Absolutely.
Okay.
Yeah. So like the pipeline, because it has to be executable, everything has to actually work.
Yeah.
The pipeline is complete. Like, you enter the lane side, it emits a term, then you generate the SMT formula from the term. You call the solver, parse back the result, extract the counterexample, and give it back to you. Yes.
So I have a question how this is actually used in production. So just a few slides ago, you mentioned that basically you pass over the entity model and the resource and the user to the Rust backend.
Mm-hmm.
And is that okay to do in production? Because I mean, doing the rules are straightforward, but then fetching the entity model, given us like all the positive types, you have to fetch the entire entity model, which can be pretty large. Is that okay?
You don't have to touch the type. So I did not talk about that at all in this talk. But we have several ways to make this easier for you. The simplest one to describe, so I'm going to describe that one. There's a more complicated one, and then there's an intern right now working on proving the more complicated one correct. But the simple one, the one which we've proven correct, is you can actually extend our type checker, and we have, to not only check that things are type correct, but that you can pull all of the data that you need within a certain number of data pools. So meaning that if you have a policy in which an attribute is of type entity, we're going to prevent you, the type checker is going to prevent you from writing an entity chain that would force the slice to pull in too much data. So for example, if you're type checking your policy at level 1, you're allowed to write, principal.friend is equal to Alice. Why are you allowed to do that? Well, because you only pull in one level, principal data. I actually don't need to know anything about the friend. I don't need to know its attributes or its ancestors. I only know its identity to write this constraint. But if you try to write principal.friend.name, the type checker would say no. This is not a level 1 policy. You can't actually evaluate this policy correctly by only pulling in the principal and resource data. You actually have to chase more pointers. So we modified the type checker to limit the amount of pointer chasing that you need to do during the entity slicing. And we give you an algorithm that, once you pass this type checking level, type checking, that's what we call it, is going to pull in enough data to evaluate this for you. But it's a good question. It is a real problem, and we have several solutions for it. Yes.
Does this work with recursive permission binding? So for example, if you have two objects, one of which is like the parent folder, another, and you have some permissions associated with the parent folder, and you want the child to essentially inherit all of the access policies of the parent subject to perhaps some other changes, like is there a way to recursively go off the tree and really define?
Not in Cedar itself. So this is, if you're building your own application and you needed this sort of hierarchical permissions, you will do it on the application side. So Cedar itself is completely stateless, and there is no search, and there is nothing recursive in it for two reasons: performance, and the other one is our ability to translate it to SMT. No loops, no recursion of any kind. So everything that's stateful or loopy, you keep outside of the Cedar within your application. Yes.
Sorry. The reason that you have to random test against the lean specification is that you are not sure that the lean specification translates directly to the Rust code, right? And so I was wondering, why didn't you use ROC, right? Like we have translation, we have Rust build, we have all of that tools about Rust inside ROC that we can use to make sure that we don't need to random test and the specification is directly.
Sorry, I didn't get the rest of which you said.
So
there's
I'm saying the problem that you have, the reason that you have to random test against lean specification is that you are not sure that the lean specification is according to the Rust code that you have. But if you were using ROC, you have all of the tools that have been built in the last years, like Rust built, like the translation that you could use to make this process easier. Is that any specific reason that you are using lean instead of ROC while the base code is Rust, and there have been a long ongoing research into that?
But you can't generate Rust codes from ROC, right?
I guess the opposite is true, right? You can convert Rust codes.
You can also convert Rust code to lean, but the problem with all of those approaches is that they are highly unstable. So if you're injecting a complicated imperative implementation into something like lean, the tool tries, it does its best to generate lean code that you can look at and prove something about. But if anything changes directly to implementation, then the reverse extraction again might have a really bad effect that's going to break all of your proofs in a way that's going to be very hard to fix. So anything that's trying to connect directly an imperative program, an efficient imperative program with lean or ROC that is doing this injection suffers from this problem. There are several efforts that are doing something like that with Isabel, and all of that is actually quite hard to do. So it's worth doing when you are working on a system that's not going to change very often. That is not the case for Cedar. So we had to come up with a pragmatic compromise, something that we can move very quickly with and that can evolve as the language evolves and get all the nice properties that we have. The thing that I think might work with that idea is if you have some sort of an intermediate layer, right? So if you had a functional specification in Rust that's not going to change very often, and then you're proving the implementation correctly with functional specification, injecting that into lean, then you would just need to trust that injection, and I think that would work. But again, all of this is very hard. I would love to have it. If you build that tool, I will use it. But until then, we have to stick with a pragmatic approach. Yes.
Yeah, so a question. So how much effort it took to build this whole infrastructure? Because like for different verification projects, like a SEL flow, how much effort it takes. For other projects, how much it took in this case?
How much effort it took in this case? So I can tell you at least some. I can give you some data points about the symbolic compiler because it was one person building it, and I kept track of all the minutes, the minute accuracy that I spent on the proof. It turns out that the entire proof took about 500 hours total. So it's not, I didn't sit down for 500 hours, but over several months it was about 500 hours. And even though the proof to code ratio looks bad, it's like 13:1. I mean, I guess it's not bad, it's pretty standard for these complex material proofs. The effort ratio is much lower than that, which basically tells you that this proof to code ratio is not a good way to measure verification efforts. So when I collected all the timing data and I compared the amount of time it took me to write the code and the amount of time to prove it, the actual proof effort was more like 5:1. So it's not that bad. Yes.
So you mentioned that you're experimenting with using Keras for Cedar. So my very high level understanding is Keras specify what you want your Rust code to do, and then you can prove stuff. Could you share
have very much experience. We have one intern who started a few weeks ago, and he has been able to produce one proof. That was one of the simple proofs. That's the one that says that the authorizer is correct, like the bid trustees, that sort of thing. In my experience, I have actually done, before doing the symbolic compiler soundness with Emina, I've actually done a proof of soundness of the symbolic compiler in Daphne, which is very similar to Rust. Rust very slow. And in my experience, it is very difficult to make those proofs stable. They tend to become very brittle because of the way the SMP solvers work. Also, for anything that we want to do meta-theoretical proofs about, I would recommend using meta-theoretical. But, use something like Ferris or Rust if you're trying to prove that a really tricky imperative implementation satisfies this nice beautiful functional specification. But meta-theory on top of functional specification, I would use an interactive theory. All right, well, thank you very much for your attention. It's been a pleasure to see you.